Hello, new geometric fact finders. That's right. We got a proof in front of us right here. This proof we did on Wednesday, actually, where we proved a fact in class with one another. Now, I kind of did this one in class with you guys here. Had you guys kind of give me the ideas. I know a lot of people kind of donated their answers to us here, and we got this proof kind of written. So I wanted to do it again, so you actually have a record of what it was we did in class, and also because the way to get better at proofs is to see examples of them. Now, obviously, if we're in class for 35 minutes, I can't go through many proofs with you guys here. So it'll probably come in video form, and we'll hopefully make them kind of quick here too. Okay, anyways, we got our proof here. So sometimes it's helpful to kind of go through what our game plan of the proof is. This proof is, well, if C is the midpoint of segment AB, then we want to prove that AB must be equal to 2 times by distance BC, right? Distance B here, C here. So if we kind of inspect what's going on a little bit, one thing I'd kind of recommend whenever you're starting a proof actually is to kind of mark up what you know. And it says here that C is the midpoint of segment AB. So actually, I'm going to just mark this up and mark this up right here because I know, for instance, if I'm being told C is the midpoint of segment AB, I know that a midpoint creates 2 congruent segments right here. So this would be one thing I want to say in my proof actually, right? C is the midpoint of segment AB. Might as well mark that up because at some point I want to say AC equals CB, because that's that's going to help me get to this that I want to prove here. But I know that because C is the midpoint, so I can sort of mark that one up here. Okay, and then also we have AB right here. So AB is this distance here, the distance between points A and B, or segment AB's length. And the length of it, we want to prove that the length of the whole segment equals 2 times this length right here, length CB. If we double this, we should be able to get length equal to length AB to prove, in fact, that a part of a segment that's created by its midpoint of the larger segment is equal to 1/2 this length here. Or you double it, you get the whole segment. Okay, you get the idea. All right, quick reminders on kind of the anatomy of what you start with and what we're going to be working with today. Because again, this is what we're trying to prove. Right? This is what we're trying to get to. We're going to try to get to say this in the proof here, right? This is what we're trying to establish. And here are the things that we have at our disposal to get us there, to help us get us there. This is what we start with, okay? We start with this right here, and it's marked given right here, but I call it something a little bit more specific. I call it the given premise. It's the premise of the problem. It's what we start with. Well, we start in a world that C is the midpoint of segment AB. That's what the math gods have told us about this situation over here. I'm going to go ahead and circle it. This is the given diagram. All right, so to get sort of to string together your reasons in order to get us to prove this statement right here, we're going to use things from the given premise, and we're going to use information that we can deduce from the given diagram, right? If we're given, this diagram is given to us, that's sort of our beginning assumption that we have a diagram like this. What is the things that we can deduce from it? What are things that we're allowed to say from it, say about this, because we have rules and definitions that allow us to say things in geometry, okay? All right, first step is pretty much 90% of the time you're going to talk about the given premise. So first step is going to be given. And so given C is the midpoint of segment AB. That's how I'd start with someone. That's really the only way to start this one right now. Well, there's another way, but we'll learn that later. All right, step 2. So C is the midpoint of segment AB. So here's where I normally do is if you introduce something in the given premise, think about what this given premise, what mathematically we can say about that. What's something that we can deduce from this, right? We start with this as our beginning assumption that this must be a fact. So it's given to us by the math gods. What's one thing that we can deduce from it? C is the midpoint of segment AB. Do we have any facts, rules, or definitions so far that we've studied so far about midpoints? Well, of course, we've studied the definition of a midpoint. So definition of midpoint is that a midpoint creates 2 congruent segments out of the original segment that it's the midpoint of here, okay? So if C is the midpoint of segment AB, I know that the distance from A to C, so from the end point of this segment to the midpoint, is going to be the same as the midpoint C to the end point of the segment here, B. CB equals AC, right? Equals AC, or BC equals AC. It doesn't matter which order these points go in here. That's definition of midpoint, okay? So I started with my given premise. I built on it, right? What could I deduce from that given premise? And I provided a reason with like how I got from step 1 to step 2. My justification is I took this information here. C is the midpoint of segment AB, and I'm allowed to establish that that those distances need to be the same by definition of the midpoint. Okay, so now I can think, how can I mess with AC BC to get me closer to my proof statement here? Because this is my if, right? If C is the midpoint of segment AB, then I want to get to this. Then AB must be equal to 2BC. So how can we prove it's going to follow from this? Well, you have AC equals BC right here. That's a fairly simple equation. Is there any way we can really modify this to sort of help us here? Well, we could multiply 2 by both sides, but, that would get 2BC. That's nice, but, we're not. What haven't we talked about here? So here's kind of where, at this point here, you might look at this here and be like, and ask yourself, how do I say things that are in conclusion, that are in the conclusion? Because, right, our conclusion of this is going to be our ending statement right here. So in fact, I could actually put this down here. My ending statement is going to be, in step 4, is going to be AB is equal to 2BC. So that's what I need to get to. Have I, in my proof, yet said anything about BC? Well, yes, I have. It says something about BC up here. Have I said anything about AB? This right here, AB right here. Have I said anything about it yet? No. Okay, no, I haven't said anything about AB. Here's where your given diagram comes into play right now. So here, we followed our given premise. We ended kind of at a dead end. There's nothing else we can say right here. We shift our attention to the given diagram right up here, okay? And what we're going to do is realize that there is something we can say about this distance here, right? This is AB right here, and AB is the whole segment, right? The length of AB here represents the length of the whole segment. How does the whole relate to its parts? Because this is part length BC, and this is part length AC. Well, how does it relate? Well, we know because we have an additional, an introductory assumption that we have with segments. We have a part plus part equals whole assumption here. The part of the segment plus its adjacent, the segment right next to it, and if we're talking about one full segment right here, part plus part equals whole. Part of the length of the segment plus the other part of the length of the segment equals the part of the length of the whole segment. And so that's what we're going to go to in step 3 right here, except we're going to clean it up with the letters here. So we're going to do AC plus BC is equal to AB. Part plus part equals whole, What's my justification for that? Well, this was a rule. This was something that, well, it's common sense, right? This length plus that length, well, it's got to equal that length, okay? Well, how can you prove it? How can you be sure about that? Well, it's common sense. So this is the kind of thing that some of the early geometry field folks, early math people folks be like, well, we can't prove this. This isn't a fact. That's not a fact that follows from anything we've assumed so far. So this is another assumption. This is a postulate here. So what we have here, it's not the angle addition postulate because we're not talking about angles. We were talking about segments, okay? So this is the segment addition postulate. All right, 3 steps down. Last one to go. Okay, so one thing I also wanted to be highly call out, right? Here, right, we started talking about given premise. I'm going to mark this GP right here. We started by talking about given premise right here. We built on it and got to here. We kind of hit like a dead ends right there after that. Where did we get this information from? So we built on our given premise. Then we need to talk about something else. We talk about our given diagram. Right? This is from the given diagram, right? Given diagram right here. And we have this being said right here. So now we got to look at this and be like, how does that get us closer to what it is we want to prove? Well, here I have AC plus BC equals AB. Excellent. AB is in the conclusion of the proof. I want this to be as my last step. I want to have AB in here. And look, I actually have AC and BC right here. That's good because AB equals 2BC. So here, BC equals AB. I have an AC over here. Question, can I change that AC to another BC? Because if I have this, right, if this is no longer AC and this is BC, check it out. This would be BC plus BC equals AB. And BC 2 times is BC plus BC. So this would be 2BC right here, right? BC plus BC. So the length BC, right, is a variable. It's an unknown length, right? It's just sort of representative of the problem. So it's like a variable. It's like X in algebra. So this is kind of like X plus X equals AB, or 2x equals AB, because x plus x equals 2x. Anyways, BC plus BC would equal 2BC here. So let's get rid of that out of the way here, because we're not talking about BC in step 3. The question is, how can I go from this step right here and modify this one to make it become what we're trying to say here, which is AB equals 2BC. So what you can do there is you can do this, right? You can take BC here because it equals AC, and AC is down there. And remember, if something is equal to another thing, then that thing can replace the other in another equation here. So, and that is called the substitution. This thing can be substituted into that equation. And notice here, this is substitution, not transitive, because BC is going in for only part of the side of an equation right here. And here we have 4 unique things being said. AC equals BC, AC plus BC equals AB. 4 unique kind of statements within 2 equations here. So this is substitution, not transitive, right? Not transitive. Transitive is when you only have 3. Anyways, I'll keep saying that again and again and again. Okie dokie, BC goes in for AC. You got BC plus BC is equal to AB, and that justification is the substitution property of equality. And yeah, that one right there is pretty sweet, because this is pretty much, we're saying the same thing here. If you wanted a 5th reason, we can get a 5th reason in a second. I might as well do that if I had to ask you, what's our 5th reason in a second? So one thing I can do here, I don't need a reason for this. I can combine like terms, right? BC plus BC is just 2 times by BC. Same thing as adding to something twice is something, adding something together to one another. This adding the same thing twice is the same thing as multiplying the thing by 2 times, right? So 2BC equals AB. So if I wanted to get it to look exactly like what I was trying to prove right here, I could maybe even have an additional step if I wanted to. What's the thing that's going to allow me to say take 2BC and move it to the right side of the equation, and take AB and move it to the left side of the equation? And I know that equality would be preserved. What's that called? When we're changing sides, right? Changing sides. It's like, you know, we got this like line here, right? Line, hence line, and both sides, side doesn't matter, right? Because it's the exact same on both sides. Ooh, and things are the exact same on both sides. My left ear is like my right ear because I am symmetrical, right? Symmetrical. So that's the symmetric property of equality. So you can put that in there if you wanted this final statement to be exactly what my proof conclusion was. You can do symmetric here and just kind of switch it around. Okay. All right. So that's our proof right there. To summarize, right? We start with the given premise as the first step about 90% of the time. So that's it. We take our given premise, first step, right? First statement and kind of proving this. Every step has a reason, right? Given for first step. And as we built on here, started to see as the midpoint, the reason why I know that AC equals BC, well, definition of the midpoint. And then the chaining of reasoning gets us to the statement you want to prove, which is this, right? That's going to be the last step. The statement you want to prove is the last step of proof. And then you're done, right? You know you're done. Once you've said this in yellow here, right? Circled in yellow here, you know that you're done with the proof here. Okay. So is this the only way that people prove facts in math with these 2 columns right here? No, we're going to learn different ways we can prove things later in this year, but this is definitely one of the more structured way here. So the thing is, like, this is can be written out in paragraph form. But if you want to kind of just run through it and make sure your reasoning totally makes sense here, you can kind of like read it here as kind of a longer if-then statement. Remember, the point of this was that we wanted to show if C is the midpoint of segment AB, then AB must equal twice times this part here, right here, BC here. And so if we read through this, it should logically make sense with me. See if you can follow my logic with this here. If C is the midpoint of segment AB, and because that's a given premise to us, then AC must equal BC, because C was a midpoint, and we know by definition of midpoints that AC and CB must equal each other because 2 segments are created one another. So I said a lot right there, but what I just said was just the definition of midpoint. We just need a reason for it. And then if we've read the book, we know what that definition is. We know we're using it correctly. Anyways, but also from our given diagram, right? Given diagram, we know that AC plus BC equals AB, part plus part equals whole, because the reason why we know that, the justification we give with this is because, right, of the addition postulate, segment addition postulate. So remember, we can think of our statements as being kind of because, right? C is the midpoint of AB because it's a given premise. Then we can make the conclusion AC equals BC because It's the definition of a midpoint. But we also know that AC plus BC equals AB because of the segment addition postulate. That justifies this statement right here, this claim here. And then we also know that BC plus BC must equal AB because of the substitution property of equality, right? What we did here is we substituted information from step 2 into step 3. And sometimes that does get written down there for clarity's sake. Where did that come from? Where did the substitution come from? Well, step 2 into step 3 right here. And so finally, we know that 2BC equals AB because of combined like terms. I didn't need to say that. But finally, we know that AB must equal 2BC because the symmetric property of equality tells us that when we have a statement of equality, side doesn't matter. We can flip them around here. So to summarize, right, what we know is that C, if it's the midpoint of segment AB, then AB must equal 2BC. And we can skip all of this justification in the future because we already have this proof written for us here. That's it for me, guys. These geometry proofs, a little bit more complicated than kind of the algebra proofs we did a little bit earlier on, because those just build on themselves. We have no diagrams, but that's what makes them more fun. And that's what makes them kind of a puzzle, and you're going to get better at this stuff as the year goes along. And right once we start looking at shapes, the proofs, I think, start making a lot of sense. And it's some pretty cool stuff that's coming up here. Let me know if you have any questions. Thanks for watching. Bye.